Hi guys, I'm Arnav. I'm a tutor for PEACE, and today I'm going to be going over chapter 4.1 for Math 1A. So 4.1 is focused on maximum and minimum values. So we've earlier covered the topic of differentiation and understanding how derivatives work. Now we're going to go on to use these derivatives. And before we really go into that, it's important to question, why do we care about this stuff? So the main point of trying to figure out maximum and minimum values is for optimization. So when you design things in engineering or whatever field of study that you're focused on, there's always a question of how do we optimize for certain parameters? How do we make sure that we minimize the cost, we minimize the amount of problems that we face in either society or some sort of system? So this is a focus of design, and trying to understand how to best design things is better understood by understanding the concept of maxima and minima. So let's go over some important definitions. So we define this number c as a number in the input f, and if f of c for some function f is greater than f of x for all other values of x, then c is an absolute maximum. That's how we define it. On the other hand, if this value c yields an output that's less than all other x, then for all other values of x, c is an absolute minimum. This thing of absolute is also called global. So why is it called that? We'll take a little example here to try to understand why. So here, this example asks, what do we call c here? And in this case, we call this an absolute maxima. Why is that? Well, at this value c in whatever function we have, we find that we have a value of f of x that exceeds all other values of x. So right here, at this point, if we compare the y value to any other y values along this entire curve, it's the greatest. It's the largest that we're going to get. This is why it's called an absolute maxima. It's because for all other values of x, I'm never going to get something that's bigger than this guy. So the point of this whole thing is really to understand, how do we obtain these maximum values, and what are the techniques for doing so? So let's keep going with this. So how do we know that x equals c yields f of x that's greater or less than all other x? It may not be, right? So in this scenario, it was pretty clear. It was obvious, that right here, it's the biggest. Everywhere else is just smaller than that. On the other hand, you can take a little weirder function like this one. We don't need to define the function, but we can just show it on a graph. So here, we find that at this point, c1, we have some sort of maxima, right? On the other hand, we look right here and we find that c2 is sort of a minima. It's the least value we can get within this range. But this function may be defined for more x, which means that there's probably a curve going all the way there and some curve going up in here. We don't know how that function behaves outside of what we call this subset of the domain. As a result of that, we don't know if this is the biggest that we're ever going to get. All we know is within this subset of the domain, we get the biggest value at c1. On the other hand, the same thing follows for an absolute minima. On this fixed domain, we know that c2 is the smallest we're going to get. When we plug in c2 into our function, we get the smallest y value. Hence, this is an absolute minima on this domain. So like we said, f of c1 is greater than f of x in this domain, and the same holds for c2 being less than f of x in this domain. As a result, these are local properties. We can't say anything about the whole function. We know just for this fixed part that this property holds. So we call these local properties because they hold for smaller subsets of our entire domain. Okay, so let's keep going. Now let's try a real example with real functions, real numbers, and seeing what we get. Now for this, you're just going to have to remember one little thing that we learned earlier in algebra. That note is as follows. For a function f of x, that's defined as ax squared plus bx plus c, we know that the highest or lowest point occurs at x equals negative b over 2a. This is just a property of the quadratic formula. In fact, as we keep going, we might even be able to derive this. We might be able to find out why this is the case. But for now, let's just assume that it's true. We're going to use it for this little example. So what we know is we have f of x equals negative x times x minus 5. Also, just ignore this. This is not exactly important, but we are going to consider this specific function of negative x times x minus 5. Now, this function looks something like this on a graph. Why so? Well, the first thing to do is look for the zeros. This is always what you do when you're trying to plot. So we know that when x equals 0, we're going to get that y equals 0. As a result, we see this little y-intercept, which is also an x-intercept. Similarly, when we plug in x equals 5, we get that x minus 5 goes to 0. As a result, f of x goes to 0. Thus, we find this 0 right here. Now we can continue with this. We know that we have zeros at 0 and 5. Using the notion that the max occurs at x equals negative b over 2a, we know that that x is 2.5. Precisely, this is right in the middle of both of our coordinated zeros. This value is 2.5 right here. So now, this concept is used because we see that here, much like the graph we showed up here, this is actually a local maxima. At x equals 2.5, x is a local max. Again, why are we saying it's a local max? Well, we don't know the whole domain of this function. We've only plotted it from 0 to 5. However, in this specific example, we know how a quadratic function works. We know it doesn't have any weird behaviors after 0 and after 5. We know that's going to keep reducing all the way down to infinity, or to negative infinity, and in the same way, after x equals 5, the same will happen. So, what do we know? We know that for all other x aside from 2.5, the value that f of x yields, aka the value of it on the curve, is going to be less than whatever we got right here. In fact, we can quantify the exact amount. At 2.5, if we plug in, we get that f of 2.5 is in fact negative 2.5 multiplied by negative 2.5, which is precisely 6.25, or also written as 25 over 4. So we know that this point right here is precisely 25 over 4. Mathematically, we like to call these pairs the local, or in this case, also the absolute maxima. So when you give an answer in a question in a homework or an exam, you often like to write that the pair x comma y is a maxima. Thus, 2.5 comma 25 over 4 is a maxima. And we can specify that this maxima is in fact absolute, since we know that for all of the domain of this function, it will never exceed this value. So this is a fun example. Now, let's move on to the next thing. So, just for the sake of understanding where we're at right now, we've understood that clearly maxima and minima exist. They may be local, they may be absolute. What we don't know is how to get these in more complicated functions. We use this interesting property of quadratics to figure out that for x equals negative b over 2a, we find that there's a maxima. In the same way, we looked at the graph and sort of qualitatively figured out that this is the case, since it's the halfway point between the 0 and 5. However, not every function is as beautiful as this quadratic. We might have to use a little bit more analysis to figure it out. For that, we rely on the extreme value theorem, Fermat's theorem, and after that, the closed interval method. So let's begin with number 2, the extreme value theorem. If a function f is continuous, so just before we move on, I'd like to just specify what continuous means. It's a very deep field of mathematics, but continuous in our case is simply the notion that when you draw this function, it will always be such that you cannot lift your pencil or your pen off the paper. Thus, this function is clearly continuous. So again, if f is continuous in this open interval ab, what does this mean? Well, in this case, we could consider the open interval from 0 to 5. That means we include 0, we include 5, and we look at the domain between 0 and 5. We look at the mapping from 0 to 5 to the function f, right? So we can give a definite value c1 in this in this open interval, and a definite value c2 in this open interval, such that C1 is an absolute maxima, and C2 is an absolute minima. Like we said earlier, absolute means that for all values in such a domain, this is the biggest or the smallest, no matter where else you look. So again, if we rely on the same example, we find that between 0 and 5, our absolute maxima was at 2.5. Now, take a second to try to figure out what the minima would be in this case, or the absolute minima. If you figured it out, you'll notice that at the points 5 and 0, we hit the 0 value. In fact, for this constrained domain from 0 to 5, that is the smallest we're going to get. You cannot get less than 0. As a result, we know that the absolute minima is going to be 0, and it occurs at two different points. It occurs at x equals 0 as well as x equals 5. So that's the extreme value theorem. Let's continue to Fermat's theorem. If f, another well-defined continuous function, has a local maxima or minima at c, then if the derivative, and again, just to recall, the derivative as we've defined it earlier is this weird limit. It's the limit of h approaches 0 of f of x plus h minus f of x divided by h, which is essentially just the slope, right? It's the slope, but within a very small x value. So just so you get some intuition for that, you have a function, we cut a very thin slice, we call this difference h, and we're looking for the slope at this point. So this is also defined as the tangent line to this curve, or the slope of the tangent line. So now we understand that we have this differential, we have this derivative. So if f has a local maxima or minima at c, then if the derivative exists at x equals c, which means that when you plug in x equals c to this formula, you get a certain value that's fixed, then the maxima or minima happens at f prime of c. This is a little bit too much jargon at the moment, but we're going to look at an example to really see why this works. Before we go into the in-depth example, I just want to show the intuition for this. So consider this function. Just a simple function, no complicated stuff here. We don't care about what the line equation is. It doesn't really matter really. It's all about trying to understand the graph. So we know that this is x, this is f of x. Now we're saying that if a point is a maxima, what usually happens there? Well, if it's a maxima, we know no other value is going to exceed it, which also means that after the maxima, you can only go down. And before the maxima, you can only go down. As a result, that point must have a flat tangent line. Now, that might sound a little complicated, but here, if we consider this point, we know that for all other values before and after this point, so any value here or here, the value is going to decrease. But you notice that this tangent line, the line that touches this curve only once at the point right here, that tangent line is flat. When it comes to differentiation, we learned that one very important concept is that if any f prime of x equals 0, then the tangent line is 0, or the slope of the tangent line is 0. In this scenario, that's exactly what happens. At the maxima, we get that the slope of the tangent line is 0, which exactly maps to f prime of x equals 0, which is exactly what Fermat's theorem suggests. It says that if there is a derivative, and if that derivative at x equals c is equivalent to 0, then we know that it must be the point of the minimum. So now we have to consider this scenario. So let's look at f of x equals x squared minus 7x plus 18. And just to clarify, I think this was missing out here. The maxima or minima occurs at f prime of c, but it's such that if f prime of c equals 0, that's the condition. So the moment the derivative goes to 0 within a fixed domain or within an infinite domain, we know that at that point we have some critical number. So this is an important definition. So if f prime of x equals 0 for any x, then that x is called a critical number. And this is important because that word gets used a lot, and if you see it in homeworks or exams, you shouldn't be thrown off by it. It just means that the derivative is 0. So let's go back to our example. F of x equals x squared minus 7x plus 18. I've used another quadratic here as an example. It doesn't necessarily need to be, but it's a good example because differentiating a quadratic, as you've probably seen in earlier videos, is slightly easier than differentiating other more complicated functions. And I've also constrained the domain, which means that we are only looking at x values that are between 0 and 10. And when I say between, I also mean including 0 and 10, since this is a closed bracket, which means it's a fixed interval with the endpoints being included. Now by Fermat's theorem, if f has a maxima or minima, then we can solve for f prime of x equals 0. Now, we have to first find f prime of x. So, using our little differentiation tools, we know that x squared has a derivative of 2x, hence 2x. Negative 7x is just a linear function, so the derivative is just a slope, it's negative 7, hence the negative 7. And 18 is just a constant, so that means in a graph it's just a straight line, which means it has a derivative of 0. Thus, the derivative is 2x minus 7. And we can set that equal to 0, shift the 7 to this side, thus getting 2x equals 7, and therefore x is equivalent to 3.5. Now this is the fixed value at which f prime of x goes to 0. What does that mean? That means it's much like this point right here. It's a point where the tangent line has a slope of 0. It's also called a critical number. So all these concepts really start to relate. Now once we know c, we need to know if c is a maxima or minima. This is where we're going to need the help of another little tool. Like I say, for this we'll need the closed interval method. So let's go look at that. The closed interval method for some fixed interval AB has 3 main parts. We start with A. We first find the critical values on this interval. What does that mean? Well, we just talked about it. The critical values are the critical numbers. These are all the points within our domain such that f prime of x equals 0. So, if we had a more complicated example with this graph, so we have a curve, we have a bunch of things happening, we can see that around this point there seems to be a tangent line of 0, so let's call this guy a critical number. There's a tangent line of 0 right here, so another critical number, and yet another tangent line right here, so another critical number. Like you see, within a domain there can be multiple critical numbers, there can be infinitely many, but here we have 3. So, we now identify the 3, and after this, we have a task. So, we have the critical values on AB. We've completed A. Now, we do a little trick here. Since it is a fixed interval, we can find f of A and f of B. So again, going back to an example, in this case, A would be this value right here, and B would be this value right here, because these are the endpoints of this interval. We found that if we set f prime of x equals to 0, this is our part A. The part A suggests that this is the value at which we have a critical value. Here we have endpoints, right? This could be computed as f of A and f of B, where A is 0 and B is whatever this value is. So now we have that. We have found f of A and f of B. Now, the smallest and biggest in A and B, which I mean are these two, are the absolute minima and maxima within this fixed domain. What does that mean? What this means is, if I have this fixed function, let's actually take an even simpler example. For example, you take this curve, just a line. Now, if you consider f of x equals x, for example, we know the derivative is just 1, and 1 never equals 0. As a result of this, we know that there actually aren't any critical values within this area, which is pretty clear. We see that the tangent line never has a slope of 0. I take any point of this curve, it's always 1. That's why it's just a linear function. So, A is sort of trivial, we don't have anything. But for B, we have to consider this fixed interval. So let me define a fixed interval. Let's say this is between 0 and 5. As a result of that, we know that right here, f of 0 is just 0. At 5, f of 5 is just 5. So, what do you find? you find that if I fix this domain to 0 and 5, the biggest it gets is 5, and the smallest it gets is 0. That's what we define as the absolute minima and maxima. 0 is the absolute minima, and 5 is the absolute maxima. 0 occurs at x equals 0, and 5 occurs at x equals 5. So that's the nature of these sort of problems. You have to do these 3 steps, and you have to do them consistently. And finding the smallest and biggest will give you the absolute. But this one doesn't really show why the critical number is important. Let's look at another example. Now here, consider this. We have a function that looks something like this. If you've ever seen a bell curve or a normal curve, this is much like that. Now, this is a bit weird. We seem to have this fixed interval. Let's call it from 0 to 10 again. So here we do know that we have a critical number. Why is that? Well, the slope right here is going to be 0. Hence, this value is a critical number. And besides that, we have a smallest and we have another smallest. So we have to do step A. So step A gave us this value. Step B will give us these endpoint values. Now step C is where we compare. So we say, hey, we have this value, we have this guy, and we have this guy. We know that the biggest it's going to get is right here. So already we know that the absolute max is, let's call this C, x equals C, and you can actually plug in f of x, which is actually going to be f of C. Now, for the absolute minima, we know that the smallest it's going to get in this domain is going to be 0. It doesn't ever go below 0, which happens both at 0 and 10. So at x equals 0 or 10, f of x equals 0. So that's an example. That's basically how this whole process of the closed interval method is going to work. So going back to our example, the quadratic, by the first part, we know that we have a critical number at 3.5. And we know that when we plug that in, we get 5.75 as our value. Now we do part B. Part B is checking the endpoints. On the endpoints, you get that f of 0 is 18 and f of 10 is 48. Thus, what we do know as a result of this is that, well, the smallest we're going to get is in fact at f of c. 18 and 48 are both bigger than 5.75. So 5.75 must be an absolute minima within this domain, as I've said here. On the other hand, we can look at the absolute maximum. What's bigger between 18 and 48? Well, clearly, we have that f of 10 is greater than f of 0. So we know that 10, 48 is in fact an absolute maxima. So we know now that for this specific function, we have both an absolute maxima and an absolute minima. And this is the overall concept of maximas and minimas. So thanks for watching. Hope this